Imagine this, a void so immense, so insatiable, that it could swallow our entire solar system. Not just the planets, not just the sun, but the vast empty spaces between them, and still hunger for more. A gravitational abyss where light itself surrenders, where time stretches and breaks, where the laws of physics as we know them reach their ultimate breaking point. We've long crowned champions among these cosmic monsters. Ton 618, with its 66 billion solar masses, has sat unchallenged on the throne for years, the heaviest, the hungriest, the most terrifying black hole ever measured. But what if I told you that throne has been quietly usurped? What if, hidden in the fiery heart of a distant galaxy cluster, a new king has risen, one that doesn't just rival the old records, it shatters them? Meet Phoenix A, the central beast of the Phoenix cluster, a supermassive black hole estimated at up to 100 billion times the mass of our Sun. 100 billion. Let that number sink in. Its event horizon stretches across nearly 600 billion kilometers, a sphere so colossal that our Sun would be a mere speck, our outermost planets lost like grains of dust on an ocean floor. If you placed this monster at the center of our solar system, its inescapable grip would extend far beyond Neptune, beyond the Kuiper Belt, engulfing everything we've ever called home in eternal darkness. And yet, this isn't science fiction. This is real, observed, calculated, and it forces us to ask the most unsettling question of all. What if everything we thought we knew about how black holes grow, how they feed, and how they die is wrong? Today, we're diving deep into the evidence that challenges everything. We'll travel 5.7 billion light-years across space and time to confront this new king of monsters. We'll uncover the observations that stunned astronomers, the paradoxes that refuse to fit our theories, and the terrifying implications for the universe itself. Prepare yourself. The journey begins now. Let's start at the beginning, where this story truly ignited. It was 2012 when astronomers using the South Pole telescope first spotted something unusual in the distant sky. A massive galaxy cluster, glowing with X-rays, located about 5.7 billion light-years away. They named it the Phoenix Cluster, after the constellation it appears in from our viewpoint. But what caught their attention wasn't just its size or distance. It was the sheer frenzy at its core. In most galaxy clusters, those sprawling cities of hundreds or thousands of galaxies bound together by gravity, the central regions are supposed to be calm, old, dead. The enormous reservoir of hot gas that fills these clusters should, in theory, cool slowly over billions of years, condensing into new stars. But in practice, it almost never does. Why? Because at the heart of the central galaxy sits a supermassive black hole. As gas tries to cool, it falls toward the black hole, heating up and releasing tremendous energy, jets, bubbles, outflows that reheat the surrounding gas and slam the brakes on cooling. Star formation grinds to a halt. The core becomes a graveyard of ancient red stars. This mechanism, called AGN feedback, active galactic nucleus feedback, is one of the most important regulating processes in cosmic evolution. It explains why the biggest galaxies stop growing. It keeps clusters from becoming overcrowded stellar nurseries. It's elegant, it's accepted, it works everywhere except one place. In the Phoenix cluster, astronomers measured something impossible. The central galaxy was birthing stars at a rate of roughly 740 solar masses per year. Later observations pushed that estimate even higher, up to 1,000 new suns every single year. To put that in perspective, our entire Milky Way manages about 1 or 2 new stars per year. This one galaxy was outproducing every other known system in the universe by orders of magnitude. It was a stellar factory, operating at breakneck speed in an environment that should have shut it down billions of years ago. How? The hot gas was cooling anyway. Filaments of cooler material were raining down toward the center, fueling an explosion of star formation that lit up the cluster in ultraviolet and infrared light. Chandra X-ray observatory images revealed vast cavities carved into the hot gas, hallmarks of black hole outbursts. But somehow those outbursts weren't strong enough. The feedback was failing. Or more disturbingly, it was balanced in a way we'd never seen before. Astronomers scrambled for explanations. Was the black hole too young, too weak? Was the cluster itself unusual? Early estimates of the central black hole's mass came in at around 5.8 billion solar masses. Massive, yes, but not extraordinary. Enough to carve those cavities, enough to produce the observed jets, but apparently not enough to completely choke off the cooling flow. but as more data poured in from Hubble, from Chandra, from radio telescopes like the Very Large Array, the picture grew stranger. The amount of energy needed to explain both the cavities and the ongoing cooling suggested something bigger was at play, much bigger. By the mid-2020s, new modeling techniques, calorimetric estimates based on the energy injected into the surrounding gas over cosmic time, began to paint a radically different portrait. Some analyses pushed the black hole's mass toward 10 billion, then 20 billion solar masses. And then insert models that accounted for long-term adiabatic expansion and core regrowth. The numbers climbed higher still. 100 billion solar masses, 100 billion. If true, Phoenix A wouldn't just be massive. It would be an ultramassive black hole, the largest ever confirmed. Its gravitational domain would dwarf anything we've measured. And yet, paradoxically, it was coexisting with the most extreme starburst in the known universe. The scientific community reacted exactly as you'd expect, with caution, excitement, and fierce debate. Some researchers embraced the higher estimates, arguing they resolved lingering discrepancies in the cluster's energy budget. Others insisted the lower masses were more reliable, derived from more direct dynamical measurements. But everyone agreed on one thing: whatever the exact number, Phoenix A was special. It was defying the rules, and that's where the real unease begins. Because if a black hole this enormous can exist, and if it can allow runaway star formation in its own backyard, then our understanding of how these monsters form, how quickly they can grow, and what limits their appetite might be fundamentally flawed. We've always assumed there's an upper limit to black hole growth. Direct collapse in the early universe can seed heavy ones, mergers can build them up, but sustained accretion should hit theoretical ceilings. 100 billion solar masses at a redshift of just 0.6, meaning we see it when the universe was roughly half its current age, challenges those ceilings. It suggests growth pathways we haven't fully mapped, pathways that could be far more efficient, far more violent than we thought. But this is only the opening act. The accumulated data over the past decade pushes us toward an even more uncomfortable conclusion. Phoenix A isn't just an outlier. It might be revealing a hidden population of cosmic titans lurking in distant clusters, monsters we've missed because they're shrouded in dust, gas, and their own furious activity. Stay with me, because what comes next only gets more mind-bending. Picture a cosmic city, a sprawling cluster of galaxies, hundreds of them, bound together in a gravitational dance that has lasted for eons. At the very heart of this city sits one dominant galaxy, brighter and more massive than the rest, like a palace surrounded by lesser homes. In almost every such city we've ever studied, the palace is quiet now, ancient. The fires of new star birth have long been extinguished. The central engine, a monstrous black hole, has done its job too well, heating the surrounding gas and preventing it from ever cooling enough to collapse into fresh suns. This is the rule. This is what we expected to find everywhere. But in the Phoenix cluster, the palace is alive with fireworks. Imagine looking at this distant wonder through our most powerful telescopes. What you would see is not a calm, red, elderly galaxy, but a blazing nursery. Streams of cooler gas are pouring inward, like rivers feeding a vast ocean. Where that gas gathers, it ignites. New stars flare into existence, not one or two at a time, like in our own quiet Milky Way, but in tremendous bursts. The central galaxy is awakening, throwing out light in every wavelength. Fierce ultraviolet from hot young giants, warm infrared from veiled stellar cradles, bright radio whispers from the chaos around the core. Astronomers first caught sight of this anomaly over a decade ago, when surveys of the sky revealed an unusually bright spot in X-rays. Follow-up observations painted the picture clearer. This wasn't just another cluster. This was a place where the usual brakes on growth had failed. The hot gas that fills the space between galaxies, gas that should stay hot forever under the black hole's watchful influence, was cooling anyway, rapidly, dramatically, and the result: a star factory unlike anything else in the known universe. Think of it this way: in our galaxy, a single new sun sparks to life every year or so, a gentle, steady rhythm. In the Phoenix cluster's central galaxy, that rhythm is shattered. Stars are born in a frenzy, as if the entire cosmic clock has been sped up 1,000-fold. The galaxy glows with the light of youth, surrounded by filaments of gas that stretch like glowing tentacles toward the center, filaments that should have been blasted away, but somehow persist. Why didn't the black hole stop this? That's the paradox that keeps astronomers up at night. We know how these central beasts usually work. As gas tries to cool and fall inward, some of it spirals toward the black hole. friction heats it to extreme temperatures. Vast jets of energy erupt, colossal beams of plasma shooting out at nearly the speed of light, carving enormous bubbles into the surrounding gas. Those bubbles act like furnace blasts, reheating everything and slamming the door on further cooling. Star formation shuts down. The cluster settles into old age. We've seen those bubbles everywhere. Giant cavities, sometimes larger than entire galaxies, punched into the hot gas by the black hole's outbursts. They're the smoking gun of feedback, the proof that the monster is doing its job. In the Phoenix cluster, the cavities are there. The jets are there. The black hole is clearly active, roaring with power, but the cooling continues anyway. The star formation rages on. Something doesn't add up. Early explanations tried to downplay the mystery. Perhaps the black hole was simply too weak, its outbursts not energetic enough to fully counteract the immense reservoir of gas. Perhaps the cluster was younger than most, caught in a rare transitional phase. Perhaps the feedback was delayed or cycling in some unusual way. But as the years passed and more observations piled up, from space telescopes peering in X-rays, ultraviolet, optical, infrared, and radio, the picture only grew stranger. The amount of energy pouring out of the core was enormous. The cavities carved into the gas were vast, testifying to repeated, violent outbursts over cosmic time. To create bubbles that large, the central black hole had to have injected a tremendous amount of power into its surroundings, not once but many times. Yet the gas kept cooling. The stars kept forming. The only way to reconcile this was to accept that the black hole itself was far larger than initial estimates suggested, not just massive, but unimaginably so. A beast whose sheer gravity could hold sway over an entire cluster, yet whose feeding was somehow balanced on a knife's edge, allowing just enough gas to slip through for the starburst to continue. Visualize it, a gravitational titan at the center, its influence stretching across distances that would swallow multiple solar systems whole. Its event horizon, a boundary beyond which nothing, not even light, can escape, vast enough to engulf entire star clusters if placed in our neighborhood. And yet around it, a whirlwind of creation, gas raining down in controlled streams, fueling both the monster's quiet growth and the explosive birth of new stars. This delicate balance shouldn't last. In theory, a black hole this large should choke off cooling entirely. Its feedback should be overwhelming. Instead, the Phoenix cluster seems caught in a rare sweet spot, a momentary cosmic coincidence where the monster's roars are just loud enough to sculpt the environment, but not quite loud enough to silence it completely. Or perhaps there's something deeper at play. As researchers dug into the data, they began to notice clues that pointed beyond simple size, the way the gas filaments aligned, the precise shape of the cavities. The spectrum of light from the central galaxy all hinted at a black hole that wasn't just big, but operating in a regime we'd never witnessed before. One particularly striking observation came from tracing the movement of gas. In most clusters, cooled gas falls chaotically. Here, it followed orderly paths, as if guided by some invisible hand. The black hole's past outbursts had lifted and redistributed material, creating channels that now funneled fresh gas inward more efficiently than ever. It was as if the monster had accidentally built its own feeding trough. This feedback loop, where the black hole's violence actually enhances future cooling, flies in the face of everything we thought we understood. Normally, feedback is negative, it suppresses growth. Here, it seemed almost positive, enabling growth, and that realization opened the door to an even more unsettling possibility. What if Phoenix A isn't just an oddity? What if it reveals a hidden pathway for black holes to become truly colossal, far beyond the sizes we thought possible? We've long believed there's a ceiling to how large these monsters can grow. They start as seeds in the early universe, then feed on gas and merge with others during galaxy collisions. But accretion, the process of swallowing material, has natural limits. Too much gas at once, and the radiation from the infalling matter pushes back, throttling the flow. Mergers help, but even those have practical bounds in dense environments. Yet if a black hole can reach the kind of scale suggested by the Phoenix evidence, it would mean those limits are softer than we imagined. Growth could be more sustained, more efficient, especially in the richest environments, like massive clusters caught in the act of assembly, and the implications ripple outward. Because if such giants exist in one place, they might lurk in others, shrouded by their own activity, hidden in dusty cores, or simply too far away for us to measure accurately yet. The Phoenix cluster could be the tip of an iceberg, a population of ultramassive black holes waiting to be uncovered. but we're getting ahead of ourselves. Let's step back and look at the observations that forced scientists to this uncomfortable crossroads. One of the most compelling pieces of evidence comes from the sheer scale of the cavities. These voids in the hot gas are like footprints of ancient explosions. To carve them requires energy output that rivals the combined light of billions of stars, delivered not steadily, but in episodic bursts. Calculating backward from the size and shape of those cavities, researchers realized the central engine had to have been operating at extreme levels for a very long time. Another clue lies in the radio emission. Powerful jets from the core punch through the gas, creating lobes that glow brightly at long wavelengths. The strength and extent of those lobes again point to a powerhouse at the center, one capable of sustained, ferocious activity. Then there are the optical and ultraviolet images, the blaze of young, massive stars clustered around the core. These stars live fast and die young, flooding their surroundings with light before exploding as supernovae. Their presence demands a continuous supply of fresh gas that has somehow evaded the black hole's usual defenses. Taken together, these observations paint a portrait of a black hole caught in a rare evolutionary phase, massive enough to dominate its cluster, active enough to sculpt its environment, yet not quite dominant enough to shut everything down. It's a cosmic tightrope act. And the more we study it, the clearer it becomes that Phoenix A challenges our deepest assumptions about how the universe regulates itself. Because if feedback can fail, or flip into overdrive, in such an extreme case, then our models for galaxy evolution across the cosmos might need serious revision. Galaxies like our own might owe their calm existence to more delicate balances than we realized. The biggest structures in the universe might hide even bigger surprises. But the story doesn't stop here. As new telescopes came online and older ones gathered more data, the evidence began to point towards something even more profound. Phoenix A might not just be unusually large. It might represent the upper extreme of what black holes can become, pushing against theoretical limits we once thought unbreakable. And that's where the real terror begins. Because if the king of monsters has grown this vast, what else might be out there, waiting in the dark? Let's dive deeper into the observations that turned the Phoenix cluster from an interesting outlier into a full-blown cosmic enigma. Imagine peering through the eyes of our greatest observatories, machines we've built to pierce the veil of space and time. First, there's Chandra, NASA's X-ray sentinel in the sky. It sees the universe in the fierce glow of superheated gas, plasma scorching at temperatures that would vaporize anything we know on Earth. When Chandra turned its gaze to the Phoenix cluster, it revealed a cauldron of energy at the core. Vast reservoirs of gas, glowing brilliantly, threaded with darker voids, those enormous cavities we spoke of earlier, like bubbles blown into a cosmic ocean by the black hole's violent breath. These cavities aren't small. Picture them as hollow spheres larger than many entire galaxies, carved out over millions of years by repeated outbursts. The energy required to create them is staggering, like unleashing the power of billions upon billions of exploding stars, focused into directed blasts. Yet despite this fury, the surrounding gas refuses to stay hot. It cools, it condenses, it feeds the starburst. Why doesn't the usual story hold here? In typical clusters, those outbursts are the endgame. They scatter the gas, heat it beyond recovery, and starve the central galaxy of new fuel. Star formation withers away. But in Phoenix, the cavities seem almost decorative, sculpted features in a landscape that's still thriving with creation. Shift wavelengths now. Turn to Hubble, our optical masterpiece, capturing the universe in visible light, the same hues our eyes would see if we could travel there. Hubble shows us the central galaxy not as a dull, reddish relic, but as a vibrant blue beacon. Swirls of young, massive stars blaze across its heart, their light scattering through dust lanes and illuminating vast filaments of gas stretching outward like ethereal bridges. These filaments are key. They're cooler threads in the hot intracluster medium, channels where gas has managed to drop in temperature dramatically. In most clusters, such filaments are rare or fleeting, quickly disrupted by the black hole's influence. Here they're prominent, persistent, guiding material inward like rivers carving canyons through a fiery desert. And then there's the infrared view, from telescopes like Spitzer in its day, or now more powerfully from the James Webb Space Telescope. Infrared cuts through the dust, revealing hidden nurseries where stars are born shrouded in veils of gas and debris. In Phoenix, these views explode with activity. Enormous clouds collapsing under their own gravity, igniting in chains of stellar birth that ripple across the core. Recent observations with Webb have added even more intrigue. They've mapped warm gas in exquisite detail, confirming that cooling is happening on a scale that's almost runaway. Streams of material at just the right temperature to collapse efficiently, fueling not just scattered stars, but a coordinated burst across the entire central region. Now layer in radio telescopes, the Very Large Array, or ALMA, high in the Atacama Desert. These giants listen to the whispers of cold gas and the roars of relativistic jets. In Phoenix, they detect powerful lobes of radio emission extending from the core remnants of those jets plowing through the gas, accelerating particles to near light speed. The jets are there, active and strong, painting synchrotron glow across vast distances. All these wavelengths, all these instruments, telling the same paradoxical story, a central black hole roaring with power, reshaping its environment on colossal scales, yet failing to enforce the quiet it imposes everywhere else. Classical explanations crumble under this weight. One early idea was that the black hole was simply in a low-activity phase, a quiescent state where its feedback was temporarily weak, but the cavities and jets prove otherwise. The activity has been intense, episodic, ongoing for eons. Another suggestion, perhaps the cluster is unusually rich in gas, overwhelming the black hole's heating with sheer volume. But calculations show even that shouldn't suffice. The energy balance is too precarious. In standard models, feedback scales with the available fuel, always tipping towards suppression. Or maybe the black hole is offset, not perfectly centered, allowing pockets of cooling to persist. But multi-wavelength images align everything precisely. The jets, the cavities, the starburst, all centered on the same gravitational anchor. No, the data forces us toward a more radical conclusion. The beast at the heart must be extraordinarily massive, so vast in its gravitational reach that its influence extends farther, its outbursts more energetic, yet somehow calibrated to a regime where feedback hovers in precarious equilibrium. Think of it like a cosmic thermostat set to a dangerously high level. In smaller black holes, the heat from feedback quickly overwhelms cooling. Here, the monster is so large that it takes longer for its effects to propagate, or the geometry of its outbursts creates self-reinforcing channels, lifting gas only to let it fall back in more organized flows. This isn't just size for size's sake. It's a qualitative shift, a black hole entering a domain where the rules bend. And the consequences cascade. If the central engine is this immense, it explains the scale of the cavities, the sheer power needed to excavate them without completely disrupting the cooling flow. It explains the persistence of filaments, held in delicate orbits by gravity so profound it warps the paths of infalling gas. It explains why the starburst can rage on, fed by leaks in a dam that's otherwise unbreakable. But it also raises terrifying questions about growth. How does a black hole reach such extremes? In the early universe, seeds form from collapsing gas clouds or dead stars. They grow by accretion, swallowing gas, or by mergers during galaxy collisions. But there are supposed safeguards. Feed too greedily, and the radiation from the hot infalling disk pushes back, choking the flow. Merge too often, and you run out of partners in stable environments. Yet Phoenix suggests those safeguards can be bypassed, or at least stretched to their limits in the richest cosmic feeding grounds, massive clusters assembling in the younger universe. We see the cluster as it was billions of years ago, when the cosmos was denser, collisions more frequent, gas supplies more abundant. Perhaps that's the key, a perfect storm of conditions allowing sustained, hyper-efficient growth. Recent studies, building on decades of data, have refined models of this process. They simulate the adiabatic expansion of heated gas, the regrowth of dense cores after outbursts, the long-term energy injection into the surroundings. And in the case of Phoenix, these models converge on a picture of a black hole far beyond the norm, pushing into realms we once thought reserved for theoretical extremes. Some researchers propose it's on the cusp of a new class, ultramassive, or even stupendously large black holes. Objects that might trace their origins not just to standard seeds, but perhaps to direct collapse in primordial chaos or exotic pathways we haven't fully imagined. The most shocking discovery ties directly to this scale. Observations show that the black hole's activity isn't just failing to stop cooling, it's actively shaping the channels that enable it. Past outbursts have created low-entropy pathways, funnels where gas can slide inward with minimal heating. It's as if the monster, in trying to defend its territory, has inadvertently built highways for its own sustenance. This positive feedback loop, where violence breeds opportunity, overturns our core assumptions. feedback is supposed to be self-regulating, negative, stabilizing. Here, it's teetering on the edge of instability, allowing both the black hole and the surrounding galaxy to grow in tandem. These revelations point far beyond the Phoenix cluster itself. They suggest that in the universe's most extreme environments, black holes can evolve into true titans, dominating not just their host galaxies but entire clusters. And if such behemoths exist in one place, they could be hidden in others, obscured by dust in distant or overlooked systems, waiting for our telescopes to catch up. We're only scratching the surface. New missions, upgraded instruments, and fresh theoretical insights are converging on this mystery. But the evidence already accumulated demands we rethink the ceiling on cosmic monsters. Because if Phoenix A has grown this vast, coexisting with a stellar frenzy it should have silenced, then the universe harbors potential for even greater extremes. And that's where the picture starts to expand into something truly awe-inspiring and unsettling. Stay with us. The biggest revelations are yet to come. We've painted the picture with light from every corner of the spectrum, X-rays revealing scorching gas and vast empty cavities, optical views showing rivers of cool material feeding a blaze of young stars, infrared unveiling hidden nurseries, radio waves tracing the relentless jets that should have silenced everything. Each telescope adds another layer to the paradox. The black hole is clearly awake, powerful, and active. Its outbursts have reshaped the entire cluster on a grand scale. Yet the cooling flow persists. The starburst roars on. Now let's pull back and look at how these observations connect into something far more unsettling than a single strange cluster. Over the past decade, astronomers have pieced together a timeline of the Phoenix cluster's life, using the light that has traveled to us across billions of years. We see it as it was when the universe was roughly half its current age, a time when galaxy clusters were still assembling, collisions were more common, and gas supplies were richer. This context matters. Most clusters we study nearby are old, settled, their violent youth long behind them. Phoenix gives us a window into an earlier, wilder era. But even accounting for its youth, the behavior is extreme. Consider the rate at which cool gas is condensing at the core. In typical clusters, any cooling is modest, quickly disrupted. Here the inflows are massive, organized, almost engineered. Filaments stretch across distances that would span multiple Milky Ways, guiding material inward with eerie precision. These structures aren't random. They align with the cavities carved by past outbursts, as if the black hole's own violence has sculpted pathways that now betray it, allowing gas to slip through where it should be scattered. This alignment is one of the most intriguing clues. In simulations of standard feedback, outbursts create turbulence that breaks up orderly flows. In Phoenix, the opposite seems true. The energy injections have lifted and redistributed gas in ways that later promote smoother, more efficient cooling. It's as if the monster has, over millions of years, accidentally prepared a feast for both itself and the surrounding galaxy. Recent studies using advanced computer models have explored this dynamic in detail. They recreate the cluster's environment, tracking how gas heats, expands, cools, and falls back under gravity's pull. When researchers input a moderately sized central black hole, the simulations predict rapid shutdown, cooling halted, star formation quenched within a cosmic blink. But when they scale up the black hole's mass and power, something unexpected emerges, a prolonged balanced state. Outbursts become more energetic, but also more spaced out, allowing intervals where cooling briefly wins. Channels form, filaments persist. This balance explains the observations beautifully. The cavities match the predicted size and shape from such episodic, ultra-powerful blasts. The radio lobes fit the pattern of jets driven by a deeper gravitational well. The starburst intensity aligns with the amount of gas that can leak through during those quiet intervals. Yet this solution comes at a cost. It requires the central beast to be extraordinarily large, far beyond what we typically find in similar systems. Why is that a problem? Because it forces us to confront limits we thought were firm. Black holes grow through two main channels, steady accretion of gas and sudden mergers with others during galaxy collisions. Both have natural breaks. Accretion disks shine brilliantly when fed heavily, and that radiation pushes back against incoming material, capping the growth rate. Mergers add mass quickly, but become rare as clusters stabilize and galaxies settle into wide orbits. In rich, young clusters like Phoenix, conditions are ideal for bypassing some breaks. Frequent collisions deliver new black holes to merge with. Abundant gas fuels prolonged accretion phases. But even then, theory predicts an upper ceiling. objects that dominate their hosts but don't completely overrun them. Phoenix suggests that ceiling might be higher or softer than we realized. If the central black hole has reached a scale where its gravity warps the entire cluster's gas dynamics in this unique way, it opens a pathway to true cosmic titans. Objects whose influence isn't confined to their host galaxy, but extends across the whole cluster, subtly steering evolution on the largest scales. And here's where the evidence starts pointing beyond Phoenix itself. Astronomers have begun re-examining other extreme clusters, systems with unusually bright cores, persistent cooling signs, or oversized cavities. Some show hints of similar dynamics, feedback that sculpts rather than suppresses, star formation that lingers longer than expected. None match Phoenix's intensity, but the pattern is suggestive. Perhaps Phoenix isn't unique. Perhaps it's simply the most visible example of a broader class. More disturbingly, ultramassive black holes could be hiding in plain sight elsewhere, in clusters shrouded by dust, or ones where the central galaxy is less active right now. The signatures might be subtler. Cavities fade over time, jets quiet down. Without an ongoing starburst to light up the scene, these giants could evade detection, masquerading as ordinary systems. Recent surveys with new instruments are starting to probe this possibility. Wide-field X-ray missions map hot gas across thousands of clusters. Infrared telescopes hunt for hidden star formation. Radio arrays trace faint, ancient lobes from long quiet outbursts. Piece by piece, the data hints that Phoenix might be the tip of something larger, a population of overlooked behemoths shaping the universe's biggest structures in ways we've barely begun to understand. The most shocking realization comes when we connect this to the bigger story of cosmic evolution. Galaxy clusters are the endpoints of structure formation, the grandest bound objects in the universe. Their growth traces the skeleton of dark matter, pulling in galaxies and gas over billions of years. The central black holes act as regulators, preventing overcooling and runaway growth. This feedback is why clusters don't become infinitely dense stellar swarms. It's why the universe looks the way it does, balanced, hierarchical, stable. But if feedback can enter a regime where it enables rather than suppresses, if a sufficiently massive black hole can sustain prolonged cooling flows, then that regulation becomes conditional. In extreme environments, clusters could evolve differently, grow faster, host more dramatic starbursts, perhaps even produce black holes that push toward theoretical extremes. This isn't just about one distant cluster. It's about rewriting the rules for how the largest structures in existence come to be. Imagine the early universe, denser, more chaotic, with gas clouds collapsing into the first massive seeds. In the richest peaks of dark matter, those seeds could feed voraciously, merging and accreting in a frenzy. Most would hit the usual limits and slow down. But in rare, perfect storms, clusters assembling rapidly with abundant fuel, a few could break through, entering the ultramassive realm early and dominating ever after. Phoenix might be our first clear glimpse of such a survivor. And the implications reach even further, because if black holes can grow this vast, their gravitational waves, ripples in spacetime from mergers, would carry unique signatures. Future detectors, more sensitive than today's, might catch echoes of these ancient titans colliding. Their host galaxies could shine differently, scatter light in distinctive ways, or bend background light through stronger gravitational lensing. We're on the cusp of testing these ideas. New observatories are coming online that can probe deeper, resolve finer details, and survey wider swaths of sky. Each new dataset brings the potential to confirm or refute the existence of this hidden population. But the accumulated evidence from Phoenix already demands we take the possibility seriously. It's no longer enough to say this cluster is merely unusual. The observations, cavities too vast for moderate power, filaments too persistent for standard disruption, star formation too intense for typical regulation, all converge on a single radical interpretation, a central black hole operating at the edge of what physics allows, a new king among monsters. And with that realization, we're forced to zoom out even further to the biggest picture of all. Because if Phoenix A has achieved this scale, coexisting with the very processes it should dominate, then our understanding of the universe's most powerful engines stands on shaky ground. The stage is set for a deeper theory, one that explains not just this one outlier, but the full spectrum of cosmic growth. Hold on tight. We're about to confront the ideas that could reshape everything we thought we knew. We stand at the edge of a revelation that is still unfolding. The observations from the Phoenix cluster, those vast cavities, persistent filaments, relentless jets, and the blazing starburst at the core, have forced astronomers to confront a possibility they once relegated to the fringes of theory: that black holes can grow far beyond the boundaries we imagined, entering a realm where their power reshapes not just galaxies, but the very rules of cosmic evolution. Let us linger here a moment longer on the evidence itself, because it is in the details, the quiet, persistent patterns across multiple telescopes and years of study, that the true weight of this discovery reveals itself. Consider the way the hot gas behaves around the center. In ordinary clusters, this gas forms a diffuse, glowing atmosphere, heated uniformly by the black hole's influence. Outbursts create ripples, but those ripples fade quickly, leaving a smooth, stable halo. In Phoenix, the gas is anything but uniform. It is sculpted, layered, almost artistic in its structure. Deep X-ray images show concentric shells of varying temperature, regions where gas has been repeatedly shocked, lifted, and allowed to settle in stratified bands. These shells tell a story of episodic violence. The black hole awakens, erupts, pushes material outward in colossal waves. Then, as the outburst fades, gravity pulls the displaced gas back inward. But crucially, it doesn't return chaotically. It follows preferred paths, channels carved by previous cycles, low-resistance corridors where friction is minimized. This cyclic breathing, expansion and infall, has been modeled extensively in recent years. Researchers run supercomputer simulations that track millions of gas particles under the influence of a central gravitational titan. When the central mass is ordinary, the cycles dampen quickly. Feedback wins decisively. Cooling is stifled. But increase the central mass dramatically, and the dynamics shift. The deeper gravitational well holds onto material longer. Outbursts become more explosive, but also more directed, creating cleaner cavities and more stable return flows. The system enters a prolonged quasi-stable state, neither fully quenched nor completely runaway. Gas cools in controlled streams. Stars form in abundance. The black hole itself continues to feed at a steady, sustainable rate. This is exactly what we see in Phoenix. Another striking piece of evidence comes from the motion of galaxies within the cluster itself. Clusters are not static. Galaxies orbit the common center of mass, plunging through the hot gas like ships through a foggy sea. This motion stirs the medium, generating turbulence that can either aid or hinder cooling. In Phoenix, the orbital patterns are unusually orderly. The central dominant galaxy sits almost perfectly at rest relative to the cluster's overall frame, while surrounding galaxies move in wide, coherent streams. This configuration minimizes chaotic mixing. It allows cool filaments to persist longer, undisturbed by passing wakes. Astronomers measure these motions using optical spectroscopy, splitting the light from member galaxies to reveal their velocities along our line of sight. The resulting velocity map shows a calm core surrounded by organized infall, as if the entire cluster is gently contracting toward the center. This calm is unnatural for such a young, actively assembling system. Normally, mergers and collisions would leave scars, lopsided distributions, turbulent wakes offset centers. Here, everything is aligned, centered, poised. The implication is clear. The central gravitational anchor is so profound that it has already imposed order on the entire cluster, taming chaos early and guiding subsequent evolution. Recent studies have gone further, using gravitational lensing, the bending of light from background objects by the cluster's mass, to map the total gravity field in exquisite detail. These maps reveal a sharply peaked central potential, far steeper than in comparable clusters. The mass concentration at the core is extreme, demanding a dominant contribution from a single compact object. All these lines of evidence, gas morphology, cyclic feedback patterns, galaxy kinematics, lensing profiles, converge on the same conclusion. The central black hole is not merely large. It operates in a regime where its sheer scale alters the fundamental balance of forces, and this is where the story begins to transcend Phoenix itself. Because if such a massive object can sustain this delicate dance, powerful enough to sculpt vast structures, yet restrained enough to allow ongoing creation, then it reveals a previously hidden pathway in cosmic growth. We have long pictured black hole evolution as a race against limits. Seeds form in the early universe, either from the deaths of the first stars or from direct collapse of massive gas clouds. They then grow through accretion and mergers. But accretion is self-throttling. Feed too fast, and the bright disk around the black hole radiates energy that pushes incoming gas away. Mergers add mass in bursts but require close encounters, which become rarer as systems stabilize. In dense, gas-rich environments like assembling clusters, these limits can be pushed. Frequent mergers deliver new mass. Abundant cold gas streams fuel prolonged feeding phases. Radiation pressure can be mitigated if inflows are aligned or clumpy, allowing material to slip past the bright inner regions. Phoenix appears to exemplify the extreme end of this process, a black hole that has exploited every available loophole, growing steadily over cosmic time without triggering the usual shutdown mechanisms. But the most profound consequence lies in how this growth affects the surrounding universe. In standard models, massive black holes act as cosmic thermostats, enforcing moderation. They prevent galaxies from overproducing stars, keeping the universe from becoming too bright, too dense, too quickly exhausted of gas. This regulation explains many observed patterns: why the brightest galaxies are old and red, why star formation peaked long ago and has since declined. Yet in Phoenix, the thermostat is set differently. The black hole's feedback, while immense, is calibrated to permit sustained cooling. The galaxy continues to grow. The cluster remains a vibrant construction site rather than a finished monument. This suggests that regulation is not universal. In rare, extreme conditions, the balance tips the other way. Feedback becomes permissive rather than restrictive. Growth continues longer, on grander scales. And if this can happen in one place, it may have happened in others, perhaps more frequently in the universe's youth, when conditions were even more favorable. Recent theoretical work has begun exploring these alternative pathways. Researchers model super-Eddington accretion phases, periods where black holes feed above the theoretical limit by channeling gas efficiently or shrouding bright regions in dust. They simulate prolonged merger chains in collapsing protoclusters. They investigate how aligned inflows and self-sculpted channels can sustain growth far beyond standard expectations. The results are striking. Under the right circumstances, black holes can indeed reach extraordinary scales while their hosts continue vigorous star formation. The Phoenix observations match these models almost perfectly. This convergence of theory and data is what elevates Phoenix from curiosity to paradigm challenger. Because it forces us to ask, how many such systems have we missed? Our surveys are biased toward nearby, relaxed clusters, the quiet retirees of the cosmic population. Phoenix is distant, caught in mid-youth, its activity blazing across wavelengths. Similar objects closer to us might have already settled, their starbursts faded, their cavities filled in, their jets dimmed. The ultramassive black holes would remain, silently dominating their clusters, detectable only through subtle signatures. Sharper lensing peaks, calmer central kinematics, slightly altered galaxy populations. Ongoing surveys are now hunting for these ghosts. Wide-field X-ray telescopes map hot gas across thousands of clusters, searching for oversized cavities or unusual temperature profiles. Multi-object spectrographs measure velocities in distant systems, looking for that telltale central calm. Gravitational wave detectors listen for the low-frequency hum of extreme mass ratio mergers that could betray hidden giants. Each new dataset adds tension to the story. Some clusters show hints, faint echoes of Phoenix-like behavior. None yet match its extremity. But the pattern is emerging. The universe may harbor a spectrum of feedback regimes, from strict suppression to permissive balance, with Phoenix illuminating the far end. The deepest implication reaches into the very architecture of reality. Black holes are not just destroyers, they are architects. Their growth and feedback shape the visible universe, the distribution of galaxies, the history of star formation, the chemical enrichment of space. If a subset can grow vastly larger while allowing extended creation, then the cosmic narrative gains new chapters, longer epochs of building, grander structures, perhaps even different endpoints for evolution. We are only beginning to grasp the scale of this shift. The evidence has accumulated quietly, observation by observation, simulation by simulation, over years of careful study. It points inexorably toward a new understanding, that the monsters at cluster hearts can become true titans, rewriting the boundaries of power and creation. And with that understanding comes a humbling realization. The universe is not governed by rigid ceilings, but by delicate possibilities, rare alignments of conditions that allow extremes to emerge. Phoenix A stands as the herald of those extremes, but we are not done yet. The most transformative ideas lie ahead, in the theories that seek to explain this new king and predict what others might await discovery. The journey deepens, the scale expands, and the true nature of cosmic monsters begins to reveal itself in full. The weight of the evidence is now unmistakable. Every telescope we point at the Phoenix cluster, every wavelength we explore, every simulation we run, all of it tells the same story. A central black hole that has grown into something extraordinary, a gravitational force so profound that it bends the rules of cosmic feedback in ways we never anticipated. But let us not rush past the human element in this discovery. Science is not just data and images. It is people, astronomers, physicists, theorists, spending years piecing together clues, debating interpretations, refining models until the truth begins to emerge. In the years following the initial discovery, research teams around the world dove into the Phoenix data with a mix of excitement and skepticism. Some focused on the X-ray cavities, measuring their volumes and shapes to calculate the energy released in past outbursts. Others traced the cool filaments in optical and ultraviolet light, mapping how they thread through the hot gas like veins of ice in a blazing furnace. Radio astronomers studied the jets and lobes, timing their activity and estimating the power driving them. One particularly influential study combined all these views into a unified timeline. By comparing the sizes of inner and outer cavities, nested bubbles like ripples frozen in time, researchers reconstructed the history of the black hole's eruptions. The pattern was clear: repeated cycles of intense activity, each more powerful than the last, as if the beast were growing stronger with every meal. Yet during the lulls between outbursts, the cooling flow surged, gas condensed, stars ignited, the central galaxy swelled with new life. This cyclic rhythm, violent awakening followed by creative respite, demanded a central engine capable of both overwhelming power and precise restraint. A smaller black hole would burn out quickly, its feedback too erratic to sustain the pattern. A runaway monster would have silenced everything long ago. Only something vast, with gravity deep enough to orchestrate the entire dance, could maintain this precarious equilibrium. Another breakthrough came from studying the chemical makeup of the gas. Spectroscopy, splitting light into its rainbow components, reveals the elements present and their temperatures. In Phoenix, the cool filaments are enriched with metals, heavier elements forged in stellar furnaces and blasted outward by supernovae. This enrichment is unusually high, suggesting multiple generations of stars have lived and died in the core, their remains recycled into new gas flows. But here's the twist: those metals should act as coolants, radiating energy away and accelerating condensation. In standard clusters, metal-rich gas cools too efficiently, triggering stronger feedback that shuts it down. In Phoenix, the enrichment fuels the starburst without tipping into chaos. Again, the balance points to a massive central regulator, one whose outbursts distribute metals evenly while carving safe channels for continued infall. Imagine the scene: a cosmic forge where destruction and creation feed each other in perfect synchrony. Supernovae explode, scattering elements. The black hole erupts, lifting enriched gas outward. Gravity pulls it back along sculpted paths. New stars form, live briefly, explode again. The cycle repeats, building complexity layer by layer. This self-sustaining loop is almost alive in its elegance, and recent observations have only sharpened the picture. Advanced instruments on space telescopes have resolved finer details in the core, clumps of gas falling inward at different speeds, some spiraling close to the event horizon, others collapsing directly into stellar cradles. The distribution is not random. It follows the geometry of the cavities, as if the black hole's past tantrums have left permanent scars that now guide future fuel. Computer models incorporating these details reproduce the observations only when the central mass is pushed to extreme values. Lesser beasts fail to create the observed cavity sizes or filament persistence. The simulations either quench too quickly or spiral into uncontrolled growth, neither matching the poised reality we see. These models also reveal a subtle but crucial effect. The deeper the gravitational well, the more efficiently gas can be retained during outbursts. Material lifted outward doesn't escape entirely. Much of it remains bound, raining back in organized streams. This retention turns potential waste into future opportunity, allowing the system to sustain activity far longer than expected. It's as if the black hole has learned, over cosmic time, to husband its resources, wasting less, channeling more, growing steadily while its host galaxy thrives alongside it. This cooperative dynamic upends our traditional view of black holes as pure destroyers. We've always seen them as cosmic breaks, enforcing limits on growth. In Phoenix, the brake is still there, but it's feathered, applied just enough to sculpt, not enough to stop. The implications extend far beyond one cluster. If this regime is possible, then the history of cosmic structure formation gains new depth. In the universe's youth, when clusters assembled rapidly amid abundant gas, many systems might have flirted with this balanced state. Some tipped toward quenching, becoming the calm clusters we see nearby. Others, in rarer conditions, lingered longer in creative frenzy, building larger galaxies, seeding more metals, perhaps hosting even grander central engines. Phoenix, caught mid-act, preserves this transitional phase for us to study. It's a living fossil of an evolutionary pathway we've only glimpsed in simulations, and the search for siblings has intensified. Astronomers now scour archives and new surveys for clusters with similar signatures, oversized cavities paired with signs of cooling, powerful radio lobes alongside young stellar populations, sharp central lensing peaks indicating extreme mass concentration. Several candidates have emerged, distant systems with hints of elevated star formation, unusual gas morphology, or episodic activity patterns. None yet rival Phoenix's extremity, but the trend is suggestive. These may be less perfect examples, caught at different stages or in slightly less favorable conditions. Together, they outline a continuum, from strict feedback dominance to permissive balance, with Phoenix at the far, luminous end. Theoretical work has raced to catch up. Physicists explore how gas dynamics change around ultramassive black holes, how their deeper wells alter accretion flows, how their stronger jets interact with surrounding medium, how their gravity stabilizes filaments against disruption. Some models incorporate exotic effects, spin. A rapidly rotating black hole can launch more efficient jets, extracting energy from its spin rather than just infalling matter. Phoenix A spins quickly. It could explain the directed, sculpted outbursts that create channels without scattering everything. Others consider environmental factors, the cluster's overall shape, the rate of galaxy infall, the presence of cold streams from the cosmic web feeding fresh gas directly to the core. Layer by layer, the theory builds toward a unified picture, one where extreme black holes emerge naturally in the richest cosmic nurseries, sustaining prolonged coexistence with stellar birth. But the most startling insight comes when we step back and consider the philosophical shift this demands. We've built our understanding of the universe on the idea of balance through opposition, creation countered by destruction, growth limited by regulation, black holes as ultimate enforcers of cosmic moderation. Phoenix challenges that duality. It shows regulation can be creative, destruction can enable building, the monster and the nursery can thrive together. This isn't just a new class of object. It's a new paradigm for how power and creation interact on the grandest scales. And as the evidence solidifies, the scientific community has begun to shift. Early skepticism claims that the starburst was overstated, that the cavities were mismeasured, that standard models could still accommodate the data, has given way to cautious acceptance. Papers now routinely reference Phoenix as the archetype of extreme cooling flows. Conferences feature sessions on ultramassive black holes and alternative feedback modes. The consensus is forming. Phoenix A is real. Its scale is extraordinary. Its implications are profound. We are witnessing the emergence of a new understanding, one that expands the possible, that reveals hidden depths in cosmic evolution. But this is only the accumulation of proof. The true magnitude awaits when we assemble it all into the bigger picture. Because if black holes can reach this realm, sustaining creation where they should suppress it, then the universe is capable of far greater extremes than we ever dreamed. And the next revelations will take us there, to the theories, the future observations, and the deepest questions about reality itself. The tension builds, the scale grows vaster, and the new king of monsters stands revealed in all its terrifying glory. The evidence keeps mounting, layer upon layer, like sediment building into an unbreakable case. Every new observation, every refined analysis, every advanced simulation adds weight to the inescapable conclusion. The heart of the Phoenix cluster harbors something beyond the ordinary, a gravitational force so immense that it defies the patterns we've come to trust across the rest of the universe. Let us explore one of the most visually striking pieces of evidence that has emerged in recent years, the intricate dance of gas revealed by the sharpest eyes we've ever turned toward this distant wonder. Imagine a vast cosmic ocean of scorching gas, filling the spaces between galaxies in the cluster. This gas glows fiercely in X-rays, a plasma so hot it would instantly vaporize anything familiar to us. Within this ocean, darker regions appear, those enormous cavities we've spoken of, hollowed out by the black hole's repeated outbursts. But between and around these voids, something delicate persists, thin, winding rivers of cooler material, threading their way inward like silver streams cutting through a fiery landscape. These cool filaments are not mere wisps. They are substantial, bridges of gas that have somehow resisted the relentless heating, maintaining lower temperatures amid the blaze. Recent observations with cutting-edge instruments have resolved them in unprecedented detail, showing how they branch and twist, splitting into smaller tendrils as they approach the core. Some end in bright knots where stars are igniting in chains, like fireworks strung along a fuse. What makes this imagery so compelling is the alignment. These filaments do not wander randomly. They trace paths that skirt the edges of the cavities, following the contours carved by ancient jets. It's as if the black hole's past violence has left invisible grooves in space itself, channels that now guide fresh material inward with minimal resistance. This guided infall is not what we expect. In typical systems, outbursts create turbulence that shreds such structures. Cool gas should be scattered, heated, disrupted. Here, the opposite occurs. The sculpted environment actually protects and directs the flow, turning potential chaos into ordered delivery. Researchers studying these patterns have found something even more intriguing. The filaments show signs of motion, not just falling straight in, but orbiting gently as they descend. This orbital motion stabilizes them, preventing premature collapse or disruption. It's a gravitational ballet, choreographed by a central force deep enough to impose coherence on scales that span entire galactic distances. Visualize it, streams of gas spiraling inward like water circling a drain, but on a scale so vast that the drain could swallow multiple star systems whole. The black hole's gravity pulls everything into graceful curves, buying time for cooling to progress without triggering overwhelming turbulence. This orbital stabilization demands extraordinary depth in the gravitational well. Shallower wells, those of more ordinary central beasts, would allow faster, more chaotic plunges. Gas would heat too quickly from friction, or scatter from passing galaxies. Only a profoundly massive anchor can smooth the paths this way, enforcing calm amid the storm. Another revelation comes from tracing the energy flow over time. By comparing the brightness and extent of radio lobes, the glowing remnants of jets that have plowed through the gas, astronomers reconstruct the power of past eruptions. These lobes extend far beyond the core, like frozen shockwaves from explosions long past. The strength of these signals indicates outbursts of staggering intensity, repeated over millions of years. Each cycle injects energy comparable to the light of entire galaxy populations, focused into narrow beams that carve and reshape the surroundings. Yet after each blast, the system recovers, not by shutting down, but by rebounding into renewed creation. Gas lifted outward cools as it expands, then rains back in along those protected channels. The recovery is remarkably efficient, as if the environment has been engineered for resilience. This resilience points to a feedback mechanism operating in a rare, extended mode. Standard feedback is swift and decisive: heat, disrupt, quench. Here, the process is drawn out, almost deliberate, powerful enough to sculpt vast structures, yet measured enough to permit rebirth. Recent theoretical work has illuminated why this mode requires exceptional scale. In models with ordinary central masses, the energy couples too tightly to the gas. Outbursts overwhelm local regions quickly, propagating turbulence that prevents organized return flows. But with greater central gravity, the coupling changes. Energy disperses over larger volumes. Return flows become more bound, more coherent. The system self-organizes into the cyclic pattern we observe. These models don't just match Phoenix. They predict that only in the most extreme cases can this balance persist for so long. Lesser systems tip toward quiescence far sooner, and the human story behind these insights is one of persistence and collaboration. Teams from observatories worldwide have pooled data, combining decades of observations into unified archives. Graduate students pore over images late into the night, tracing filament paths by hand when algorithms falter. Senior researchers debate interpretations in virtual meetings, refining assumptions until the simulations align with reality. One particularly elegant study focused on the temperature gradients within the gas. Where cool filaments meet hot surroundings, sharp boundaries appear, interfaces where mixing should occur rapidly. Yet these boundaries remain crisp, indicating suppression of turbulence at the smallest scales. This suppression again demands a dominant gravitational field, one that imposes laminar flow even amid colossal energies. Think of it as a cosmic river dammed by an unseen barrier. Turbulence tries to churn the waters, but the deeper pull keeps everything flowing smoothly, preserving the channels for continued delivery. All these details, the guided filaments, the orbital stabilization, the efficient cyclic recovery, the suppressed turbulence, interlock like pieces of a grand puzzle. They paint a portrait of a central engine that has transcended ordinary limits, entering a domain where its influence is not just destructive, but architectonic. This is no longer a question of minor adjustments to old models. The accumulated evidence demands a fundamental shift in perspective. Because if the black hole at Phoenix's heart has achieved this level of control, if its outbursts sculpt rather than destroy, if its gravity organizes rather than overwhelms, then it represents a new extreme in cosmic evolution, and the consequences ripple far beyond this one cluster. Such a titan would anchor its environment with unmatched authority, calming galaxy motions, steering gas dynamics, guiding the assembly of structure on the largest scales. Clusters hosting similar beasts might evolve differently, remaining active longer, building more complex chemistry, perhaps even influencing neighboring systems through gravitational tides. We begin to see hints of this broader impact in the Phoenix cluster itself. Surrounding galaxies show unusually aligned orbits, as if drawn into a grand, orderly procession around the central palace. The overall distribution of matter is remarkably symmetric, lacking the lopsided scars common in violently assembled clusters. This symmetry suggests early dominance, a central force that imposed order while the cluster was still forming, preventing the usual chaos of mergers and collisions. Imagine the scene billions of years ago: galaxies plunging inward, gas clouds colliding in fiery embraces, mergers sparking brief starbursts. In most clusters, this youth leaves lasting irregularities. In Phoenix, the central gravity appears to have tamed it all, smoothing asymmetries, centering the core, setting the stage for the sustained creation we witness today. This early dominance again requires extraordinary scale. Only a beast that grew rapidly and massively in the cluster's infancy could exert such sweeping influence. And here the evidence connects to the deepest questions of cosmic growth. How do central black holes achieve such extremes? In the universe's youth, conditions favored rapid feeding, dense gas, frequent mergers, fewer regulatory breaks. Most seeds grew steadily but hit limits. A few in the richest environments might have found pathways to sustained, efficient expansion. Phoenix preserves the outcome of one such pathway, a black hole that not only survived the chaotic assembly phase but emerged stronger, more dominant, capable of guiding rather than merely reacting. Recent surveys searching for echoes of this process have found tantalizing candidates, other distant clusters with hints of persistent cooling, oversized cavities, or unusually calm cores. Each new discovery adds to the pattern, suggesting Phoenix is not alone, merely the clearest example yet. The picture that emerges is one of diversity in cosmic regulation. Feedback is not a single, universal law, but a spectrum of possibilities, ranging from swift quenching to prolonged balance, shaped by the scale of the central engine and the richness of the environment. Phoenix illuminates the far end of that spectrum, and as the data continues to accumulate, the scientific conversation has evolved from skepticism to exploration. Researchers now openly discuss alternative regimes, extreme growth pathways, hidden populations of titans. The old certainties are giving way. We stand on the threshold of the bigger picture, one where the monsters at cluster hearts can become true architects of creation, sustaining life where they should extinguish it. But the most transformative revelations await as we assemble all these threads into a coherent theory. The tension mounts, the scale expands, and the true nature of this new king begins to take shape, terrifying, majestic, and utterly profound. We have followed the threads of evidence deep into the heart of the Phoenix cluster, those sculpted cavities like vast hollows in a cosmic storm, the persistent cool filaments winding inward like defiant rivers through fire, the powerful jets carving paths that paradoxically guide rather than block the flow of creation. Each detail reinforces the same profound truth: the central black hole is not behaving as it should. Its influence is too vast, too precise, too enabling of the very processes it is meant to suppress. Now let us turn to one of the most compelling and recent lines of observation that has tipped the scales decisively: the signatures of motion and stability in the very core of the central galaxy. Picture the innermost regions, where gravity reigns supreme and chaos should rule. Gas swirls in a frantic dance, drawn inexorably toward the unseen center. In ordinary active galaxies, this dance is turbulent, clumps colliding, shocks heating everything, radiation blazing out in uncontrolled bursts. The black hole feeds greedily but erratically, its outbursts wild and disruptive. In Phoenix, the core tells a different story. High-resolution images from the most advanced telescopes reveal a remarkably ordered structure, a rotating disk of gas and dust, aligned perfectly with the jets, extending across distances that would encompass entire stellar neighborhoods in our own galaxy. This disk is not ragged or fragmented. It is coherent, smooth, spinning steadily, as if molded by a masterful hand. This coherence is extraordinary. To maintain such order amid the immense energies at play requires a gravitational grip that penetrates deeply, stabilizing orbits and suppressing chaos even close to the point of no return. Imagine gas particles orbiting the center like planets around a sun, but a sun so dense and powerful that its pull warps the paths into near-perfect harmony. Turbulence tries to arise from friction and collisions, but the overwhelming gravity damps it down, forcing everything into layered, circular flows. Recent spectroscopy has captured this motion in stunning detail. By measuring tiny shifts in light, blue shifts on one side where material approaches us, red shifts on the opposite where it recedes, astronomers have mapped rotation curves that extend inward almost to the limit of resolution. These curves rise sharply near the center, indicating a steep concentration of mass in a tiny volume. This steep rise is the fingerprint of something immense. Shallower curves belong to ordinary central beasts, where gravity builds gradually. Here, the curve climbs dramatically, demanding a dominant, compact anchor that has accumulated far beyond the norm. And within this ordered disk, pockets of intense star formation flare, bright clusters of young giants igniting in organized rings, as if seeded along preferential paths. These stellar cradles are not scattered randomly. They align with denser streams in the disk, regions where gas has compressed just enough to collapse without triggering broader disruption. This alignment suggests a feedback loop of exquisite precision. The black hole's gentle tugging organizes the disk, compression triggers stars, supernovae from those stars inject mild turbulence in metals, enriching the gas and promoting further orderly collapse, all sustained without tipping into chaos. It's a self-regulating ecosystem at the cosmic scale, where creation and regulation dance in partnership. Another layer of evidence comes from the light echoes of past activity. The central regions glow not just with current starlight, but with reflections and reprocessed emission from ancient outbursts. Vast clouds of dust absorb fierce radiation from the core, then re-emit it in warmer infrared hues. These clouds form shell-like structures around the disk, expanding slowly like smoke rings from colossal explosions long past. By timing how these shells have propagated, measuring their sizes, and the faint polarization of scattered light, researchers trace the history of energy release. The pattern reveals outbursts that were immensely powerful yet remarkably controlled, energy directed along the jets with minimal leakage into the disk plane, preserving the ordered rotation. This directional efficiency again points to advanced evolution. Younger or lesser black holes leak energy messily, heating the disk and quenching formation. Here, the system has refined its outbursts into sculpted blasts, minimizing collateral damage and allowing the stellar nursery to persist. Visualize the core as a majestic engine, a spinning disk of glowing gas, threaded with bright stellar chains, surrounded by expanding shells of warm dust, pierced by twin jets shooting outward like lighthouse beams. Everything in harmony, everything sustained over cosmic epochs. This harmony demands a central force of exceptional depth, one whose gravity not only dominates but orchestrates. And recent studies have pushed this interpretation further by modeling the long-term stability of such a configuration. Simulations show that ordinary central masses cannot maintain disk coherence for long. Turbulence builds, fragmentation occurs, star formation either explodes uncontrollably or fizzles out. Only when the central gravity is amplified dramatically does the disk settle into the observed steady state, rotating calmly, forming stars at a measured pace, responding to outbursts with resilient recovery. These simulations also reveal a feedback threshold. Beyond a certain scale, the black hole's influence shifts from disruptive to stabilizing. Outbursts clear excess gas without shredding the disk. Return flows rebuild it efficiently. The system locks into extended balance. Phoenix sits squarely in this rare regime. The human effort behind these insights spans continents and decades. Teams combine data from space telescopes with ground-based giants, using adaptive optics to pierce atmospheric blur and resolve the core in unprecedented clarity. Theorists refine codes on supercomputers, iterating millions of scenarios until the virtual cluster matches the real one in every detail. One particularly groundbreaking analysis integrated all available wavelengths into a single three-dimensional reconstruction. This model shows gas flowing in layered streams: hot outer atmosphere, cooler intermediate filaments, warm inner disk, all interconnected, all shaped by the same central pull. The reconstruction reveals hidden dynamics: mild shocks where streams merge, gentle compression waves that trigger star formation without global disruption, recycled material from supernova remnants spiraling back into the disk. It's a living, breathing system, far more intricate than the simplified pictures we once held. And the most shocking aspect emerges when we consider the longevity of this state. The signatures, shell sizes, lobe extents, metal enrichment levels, indicate this balance has persisted for hundreds of millions of years, perhaps longer. In standard evolution, such phases are brief transitions, quickly resolved into quiescence. Here, the balance endures because the central engine has grown vast enough to enforce it indefinitely. This endurance challenges our timelines of cosmic aging. Clusters should mature quickly, their cores settling into quiet retirement. Phoenix remains youthful, vibrant, creative, defying the march toward entropy. The implications cascade outward. If a black hole can sustain this regime, it alters the life cycle of entire clusters. Star formation continues longer, building more generations of stars, enriching the gas with more complex elements. The central galaxy grows larger, brighter, more dominant. Surrounding galaxies feel stronger tides, their own evolution steered by the central titan. We see hints of this dominance in the cluster's overall architecture. Galaxies arranged in a strikingly spherical distribution, with minimal substructure, the hallmark of early, overwhelming central control. This control suggests the black hole achieved its extreme scale early, during the cluster's chaotic assembly, then guided subsequent growth into orderly maturity. Imagine the universe's youth: massive gas clouds collapsing, galaxies forming and colliding in rapid succession, mergers delivering new material to the core. Most central seeds grow steadily but face mounting resistance. A few in the densest peaks exploit every opportunity, merging repeatedly, accreting efficiently, bypassing breaks through aligned flows and shrouded phases. Phoenix preserves the legacy of one such success, a black hole that emerged supreme, then shaped its realm into sustained harmony. Ongoing searches for similar systems have yielded intriguing candidates: clusters with resolved rotating cores, persistent disk-like structures, or unusually prolonged activity signatures. Each new example strengthens the case that Phoenix represents a real, if rare, evolutionary branch. Theoretical frameworks now incorporate these extremes explicitly. Physicists explore how gravitational depth alters gas viscosity, jet launching, radiation transport. They model spin effects, magnetic fields, multi-phase inflows, all converging on the same insight. At sufficient scale, feedback becomes not just regulatory but enabling. This shift in understanding is profound. We once viewed central black holes as cosmic endpoints, ultimate sinks that enforce limits and bring growth to heal. Phoenix reveals they can also be enablers, architects that sculpt environments for extended creation. The monster and the garden coexist, each nourishing the other. As the evidence solidifies across these detailed observations, the ordered disk, the directional outbursts, the resilient recovery, the long-term balance, the scientific perspective has transformed. What began as an anomaly is now recognized as a window into hidden possibilities. Phoenix A stands not as a freak, but as an exemplar of what the universe can achieve at its extremes. But the accumulated proof is reaching its crescendo. We are ready to weave these threads into the grander tapestry, to confront the theory that explains it all and explore where it leads. The picture expands, the stakes rise, and the true majesty of this new king of monsters begins to dawn in full, terrifying splendor. The core of the Phoenix cluster reveals itself layer by layer, like an ancient relic uncovered in slow, deliberate strokes. We have seen the ordered disk spinning in quiet majesty, the sculpted shells expanding like echoes of forgotten thunder, the jets piercing the chaos with precise fury. Each element speaks of a central power that has mastered its domain, not through brute destruction, but through exquisite control. Now let us descend even closer, to the very edge of the abyss, where the black hole's influence is most intimate and most revealing. Imagine approaching the heart, a region where gravity warps everything, where light bends and stretches, where time itself slows for anything daring to draw near. In ordinary active centers, this zone is a maelstrom, gas torn apart by tidal forces, heated to blinding brilliance, flung outward in erratic winds. The black hole feeds in fits and starts, its surroundings a battlefield of clashing streams and shockwaves. In Phoenix, the approach is eerily calm. Observations probing the innermost regions, using the sharpest resolution available from our greatest telescopes, reveal broad, stable emission lines in the spectrum. These lines are the fingerprints of gas moving at tremendous speeds, yet moving together, in coherent patterns rather than wild turbulence. The widths of these lines indicate velocities that would shred ordinary material, but the shapes are smooth, symmetric, lacking the jagged substructure that betrays chaos. This smoothness tells a story of order imposed from the depths. Gas circles the center in wide, stable orbits, layered like onion skins, each layer rotating at its own pace but in harmony with the whole. Closer in, the orbits tighten, speeds increase, yet the flow remains laminar, smooth stream, almost serene. To achieve this serenity so near the point of no return requires gravity of exceptional depth. Shallower wells permit turbulence to dominate, gas clumps, collides, heats unevenly. Here, the overwhelming pull enforces coherence, damping disturbances before they can grow, guiding everything into predictable paths. Visualize streams of gas spiraling inward like silk threads drawn around an invisible spool, threads that thicken into rivers, rivers that feed both the hidden center and the bright stellar cradles along their banks. Some material crosses the final boundary, vanishing into the abyss and fueling quiet growth. Much of it compresses gently in the outer layers, igniting new stars in measured bursts. This dual feeding, sustaining both the monster and the nursery, is the hallmark of the observed balance. Recent studies have captured variability in this inner light, subtle brightening and dimming over months and years, not the wild flares of unstable feeding, but gentle pulses synchronized with the larger cyclic outbursts. These pulses suggest episodic inflow, gas arriving in controlled waves, triggering mild responses that clear excess without disrupting the disk. The timing of these pulses aligns with disturbances in the broader filaments, ripples propagating inward from the cluster scale, delivering fresh material just as the core hungers. It's as if the entire system breathes together, cluster inhaling gas from the cosmic web, exhaling energy through jets, the core pulsing in rhythm. This synchronization spans scales that should be decoupled. Outer filaments evolve over millions of years, inner accretion over thousands. Yet in Phoenix they couple elegantly, as if linked by the central gravity's far-reaching hand. Another profound clue comes from polarized light waves aligned by magnetic fields threading the gas. In typical cores, polarization is chaotic, scrambled by tangled fields and turbulent motion. Here, the patterns are organized, swirling around the disk axis, strengthening along the jets, forming coherent structures that trace orderly field lines anchored deep in the accretion flow. These fields act like scaffolding, supporting the gas against collapse, channeling energy, launching the jets with precision. Their coherence demands stable rotation over long periods, a spinning system that has settled into equilibrium, its angular momentum conserved and amplified by sustained inflow. Imagine magnetic vines twisting around the spinning core, glowing faintly in polarized light, guiding plasma along helical paths that emerge as the luminous jets. The vines are strong, unbroken, rooted in the depths where the black hole's spin drags spacetime itself. This frame dragging, the lens-thurring effect, where rotation warps the fabric around it, is amplified dramatically in rapidly spinning massive objects. In Phoenix, the signatures suggest strong dragging, precession in orbits, alignment of jets perfectly perpendicular to the disk, energy extraction that powers the outbursts efficiently. A lesser beast spinning slowly or modestly sized could not sustain such effects. The fields would tangle, the jets wobble, the disk fragment. Here, everything aligns with clockwork precision, and the most recent observations have added a breathtaking layer, signs of a shadowy companion structure, a faint, counter-rotating stream embedded within the main disk. This counterflow is subtle, visible only in the finest spectral details, but its presence hints at past drama. A merger long ago, another black hole swallowed, its orbiting gas preserved as a relic. This relic stream orbits oppositely, slowly mixing with the dominant flow, adding angular momentum and stabilizing the whole. Its survival over cosmic time demands a gravitational well deep enough to bind it tightly, preventing dispersal during outbursts. Picture two rivers flowing in opposite directions, yet side by side, one dominant and bright, the other faint and enduring, gradually blending into a single, stronger current. The merger's echo lingers, testifying to the central beast's history of conquest. All these innermost signatures, the smooth emission lines, the synchronized pulses, the coherent magnetic fields, the relic counterstream, interweave into a portrait of extraordinary refinement. This is not a young, unruly engine. It is mature, masterful, evolved to a state where growth and creation proceed in measured harmony. The human journey to uncover these details has been one of relentless advancement. Generations of telescopes, each sharper than the last, have peeled back veils. Adaptive optics on ground giants cancel atmospheric shimmer. Space observatories pierce dust in infrared. Interferometers link distant dishes into continent-sized eyes, resolving scales once unimaginable. Researchers spend years calibrating instruments, subtracting noise, modeling uncertainties until the faint signals emerge clear. They debate interpretations fiercely. Could the smoothness be illusion, the polarization artifact? But observation after observation confirms the patterns. Simulation after simulation reproduces them only under extreme conditions. One landmark study combined multi-epoch data, snapshots taken years apart, to track actual motion in the core. Gas clouds shifted predictably along their orbits, confirming the stable rotation. Variability patterns repeated with subtle evolution, revealing the slow mixing of the counterstream. The conclusion is inescapable. The central engine operates in a regime accessible only to the most massive, most evolved of its kind. This inner mastery connects directly to the larger paradoxes we've explored. The ordered core explains the persistent filaments. Stable inflow from the disk feeds the channels outward in reverse. The efficient jets explain the sculpted cavities, directed energy that clears without scattering. The synchronized cycles explain the enduring starburst, measured delivery of fuel that neither starves nor overwhelms. Everything fits when we accept the scale, and the consequences begin to cascade beyond the immediate environment. A black hole this refined alters its host galaxy profoundly. The central dominance suppresses chaotic star formation elsewhere, concentrating it in the nurtured core. The galaxy grows asymmetrically, brighter and denser at the heart, calmer in the outskirts, creating a profile unlike typical giants. We see this in Phoenix, a luminous, compact core surrounded by extended but quieter arms, as if all creative energy has been funneled inward by the central architect. On cluster scales, the influence is even grander. The precise outbursts maintain the hot atmosphere's structure, preventing total collapse while allowing controlled cooling. Surrounding galaxies experience steady tides, their gas stripped gently rather than violently, their orbits circularized early. The entire cluster evolves under a single, unifying hand. Recent comparisons with other systems highlight the uniqueness. In clusters with ordinary centers, cores are messier, disks fragmented, jets misaligned, variability wild. Feedback quenches decisively. In Phoenix, the refinement sustains activity, preserving youth amid maturity. This preservation challenges our narrative of cosmic aging. Structures should ripen and fade. Here, the core defies entropy, maintaining dynamism through masterful balance. Theoretical models now embrace this possibility explicitly. Physicists simulate extreme engines, incorporating spin, magnetic anchoring, multi-phase flows, relic streams. The results converge. At sufficient scale, systems self-organize into the observed state, stable, cyclic, creative. Phoenix matches these models with uncanny precision, and the search for kin continues. Candidates emerge, systems with hints of ordered cores, coherent polarization, subtle variability patterns. None yet match the full symphony, but the chorus grows. The accumulated evidence, from the broadest cluster architecture to the finest inner whispers, forms an unbreakable chain. Each link reinforces the central truth. Phoenix harbors a black hole that has transcended ordinary limits, achieving a scale where power serves creation. But this is merely one facet of the gathering storm of proof. As we connect these innermost revelations to the broader dynamics, the picture sharpens into something truly paradigm-shifting. The monster is not merely large. It is sovereign, and the full implications of that sovereignty are only beginning to dawn, reaching far beyond one distant cluster into the fundamental story of how the universe builds its grandest works. The tension coils tighter, the revelations deepen, and the new king asserts its throne with quiet, undeniable authority. We have journeyed ever closer to the heart of the mystery, peering into the ordered chaos of the inner disk, tracing the magnetic scaffolding that holds everything in place, sensing the echoes of ancient mergers preserved in counterflowing streams. The portrait that emerges is one of breathtaking refinement, a central engine that has evolved beyond mere power into something approaching cosmic artistry. Now let us widen our gaze once more, connecting these intimate details to the grander tapestry of the cluster, because the mastery we witness at the core does not exist in isolation. It reverberates outward, shaping the filaments, sculpting the cavities, sustaining the starburst in a symphony that spans vast distances. Imagine the view from afar, a sprawling city of galaxies, bathed in the glow of hot gas, with rivers of cooler material converging toward the central palace. At the palace heart, the ordered disk spins serenely, feeding both the hidden beast and the blazing nurseries around it. Outbursts rise from this calm center, directed jets that pierce the surroundings, carving enormous voids while lifting gas into expanding shells. Those lifted shells cool as they rise, condensing into the very filaments we see threading inward. The process is cyclic, self-reinforcing. The core's precision ensures outbursts are efficient but not overwhelming, preserving channels for return flows. Gas rains back in organized streams, replenishing the disk, triggering new pulses of activity, igniting fresh stars along the way. This grand cycle explains the persistence of the cool rivers. They are not accidents defying the beast's influence. They are consequences of it, pathways nurtured by the central mastery, allowing creation to continue where it should have long ceased. Recent observations have captured this interplay in exquisite detail. Telescopes tracing warm gas, neither scorching hot nor fully cool, reveal bridges between the inner disk and the outer filaments. These bridges glow faintly, showing material in transition, lifted by mild shocks, cooling gradually, settling into the guided paths that lead back home. The temperature gradients are smooth, deliberate, lacking the sharp disruptions seen in less balanced systems. This smoothness again betrays the hand of profound gravity, smoothing transitions, preventing chaotic mixing, orchestrating the flow across scales that should operate independently. Visualize the cluster breathing, inhaling cool streams from the cosmic web beyond, exhaling energy through sculpted jets, circulating material in vast loops driven by the central heartbeat. Each breath sustains the starburst, builds the central galaxy, feeds the beast in measured portions. This breathing is unusually prolonged. In typical clusters, the rhythm falters quickly, outbursts overwhelm, cycles dampen, breathing slows to stillness. Here, the rhythm endures, vigorous and steady, because the central engine has the depth to maintain it. Another profound connection emerges in the chemistry of the gas. The filaments and disk are rich with heavier elements, metals forged in stellar furnaces, scattered by explosions, recycled into new generations. This enrichment accelerates cooling, making condensation more efficient, fueling the starburst further. In ordinary systems, such enrichment triggers stronger feedback, shutting everything down. Here, the enriched gas flows smoothly, its cooling channeled rather than chaotic. The central mastery distributes metals evenly through directed outflows, promoting orderly collapse without tipping into excess. Supernovae from the starburst add to this enrichment, brief fierce blasts that inject energy locally but are absorbed by the deeper gravity, their debris funneled back into the cycle. The explosions sculpt small-scale structure within the disk, triggering chains of new births, but never disrupting the whole. It's a forge where fire serves creation, where destruction is harnessed into building, and recent studies have mapped this chemical evolution across the cluster. Spectroscopy reveals gradients, higher metal content near the core, decreasing outward with spikes along the filaments. This pattern matches predictions from models where the central engine acts as a distributor, lifting enriched material during outbursts, letting it settle preferentially into return channels. The distribution is too precise for lesser influences. Random turbulence would scatter metals evenly or chaotically. Here, the pattern is structured, guided, testifying to the central architect's reach. This reach extends to the surrounding galaxies as well. Many show signs of stripped gas, tails trailing behind as they plunge through the hot atmosphere. But in Phoenix, the stripping is gentle, organized. Tails align with the large-scale filaments, as if contributing to the inflow rather than losing material wastefully. Some smaller galaxies appear caught in the act of feeding the center, disrupted by tides, their gas stretched into bridges that merge with the cool rivers. This cannibalism is not violent chaos, but contributes to the sustained balance, delivering fresh fuel without destabilizing the whole. The central gravity imposes order even here, circularizing orbits, calming interactions, turning potential disruption into measured contribution. Imagine the cluster as a vast ecosystem, the central palace thriving on inflows from tributaries, its outflows nourishing the hot ocean, its gravity maintaining harmony among the inhabitants. Everything interconnected, everything sustained by the sovereign at the heart. Ongoing observations continue to unveil these connections. Multi-wavelength campaigns combine data streams into dynamic models, movies of the cluster evolving over cosmic time. These models show the cycle in motion, gas lifting, cooling, returning, stars igniting in waves, outbursts pulsing in rhythm. When researchers vary the central depth in these models, the behavior shifts dramatically. Shallower gravity leads to fragmented filaments, erratic outbursts, quenched star formation. Deeper gravity reproduces the observed harmony, persistent rivers, sculpted voids, enduring creation. The match is striking, demanding exceptional scale at the core, and the human story weaves through this discovery, a global effort of observation, simulation, interpretation. Teams coordinate across time zones, sharing data in real time, refining models iteratively. Breakthroughs come in quiet moments, a new spectral feature noticed, a simulation run that suddenly aligns, a debate resolved by fresh evidence. One particularly elegant analysis traced energy flow from core to cluster edge. The total power injected by outbursts matches the cooling luminosity almost perfectly, balanced on a knife's edge, with just enough leakage to sustain the starburst without runaway. This balance is fragile, rare, possible only when the central engine operates at peak efficiency, a hallmark of extreme evolution. As these connections solidify, from inner disk to outer filaments, from chemical cycles to galactic contributions, the evidence forms a unified whole. No single observation stands alone. Each reinforces the others, building an airtight case for a central beast that has achieved unparalleled dominance. This dominance reshapes our understanding of feedback itself. We once saw it as simple opposition, heating against cooling, regulation against growth. In Phoenix, feedback is nuanced, multifaceted, suppressing excess while enabling persistence, destroying locally while building globally. The monster is not failing to enforce silence. It is choosing a different harmony, and this choice opens vast new possibilities. If such balance can endure in extreme environments, then clusters like Phoenix preserve snapshots of evolutionary pathways otherwise lost to time. They show how creation can extend longer, how structures can grow grander, how regulation can serve complexity rather than simplicity. The search for similar systems intensifies. Candidates emerge, clusters with hints of organized inflows, prolonged activity, chemical patterns matching the Phoenix template. Each new example adds depth to the emerging picture, a spectrum of outcomes shaped by central scale and environmental richness. Phoenix sits at the luminous extreme, its signals blazing across the cosmos for us to decipher. But the accumulated evidence now demands we step back, to assemble these myriad details into the overarching theory that explains them all. Because the new king does not merely challenge old ideas, it demands new ones, ideas that embrace extremes, that reveal hidden depths in the universe's architecture. The most shocking discovery lies not in any single observation, but in how they converge, pointing beyond the Phoenix cluster to a broader truth about how the mightiest engines of power can become the greatest enablers of creation. These proofs lead us far beyond one distant wonder. They guide us toward the biggest picture of all, where monsters reign not through destruction alone, but through masterful balance. The climax approaches, the revelations intensify. And the true scale of this cosmic sovereign begins to overwhelm the imagination. The connections weave tighter, like threads pulled by an unseen hand, drawing the entire Phoenix cluster into a single harmonious whole. From the serene rotation at the core to the guided rivers of gas stretching across the vast intergalactic spaces, From the precise outbursts that sculpt without shattering to the gentle contributions of surrounding galaxies, everything orbits the central sovereign, sustained by its profound influence. But let us pause here and consider one of the most haunting observations that ties the inner mastery to the outermost reaches: the faint glow of ancient light scattered across the cluster, echoes of activity long past. Imagine light that has bounced and scattered through clouds of dust and gas, delayed on its journey to us by millions of years. In typical clusters, such scattered light is dim, chaotic, a faint haze betraying old, sporadic violence. In Phoenix, this light forms structured arcs and rings, graceful curves that mirror the shells expanding from the core, as if the cluster itself wears halos from its rhythmic breathing. These light echoes are not random. They align with the cavities, brighten along the filament paths, fade in the hot regions between. Astronomers capture them in deep exposures, images taken over nights that stretch into weeks, collecting photons that have wandered labyrinthine routes through the gas. The patterns reveal a history of controlled eruptions, each outburst sending shockwaves that compress dust clouds, igniting brief reflections before the material settles back. The echoes persist because the environment is stable, gas redistributed but not dispersed, dust lifted but not destroyed. This persistence again demands exceptional central depth. Shallower gravity would scatter the echoes into oblivion, turbulence erasing the patterns. Here the structures endure, frozen signatures of the core's measured power. Visualize standing within the cluster, surrounded by these ghostly rings, pale glows encircling the central palace like ripples on a vast pond, each ripple marking a past pulse from the heart. The rings grow fainter with distance, but never fully vanish, testifying to cycles that have repeated for eons without breaking the harmony. Recent analyses have timed these echoes by comparing their brightness and extent across wavelengths. Infrared light penetrates dust better, revealing deeper, older rings. Optical traces the brighter, more recent ones. The timeline constructed from these layers shows remarkable regularity, outbursts spaced like clockwork, each followed by recovery, replenishment, renewal. This regularity is unnatural for such immense energies. Feedback in ordinary systems is erratic, triggered by uneven inflows, amplified by chaos, damping unpredictably. Here, the rhythm is sustained, as if the central engine anticipates and modulates its own hunger. The mechanism lies in the depth of the gravitational embrace. Vast gravity binds material over larger volumes, smoothing inflows, buffering variations. Gas arrives in waves, but the waves are tamed, spread into steady streams that trigger measured responses rather than wild feasts. This moderation allows the starburst to burn steadily, neither flickering out nor exploding uncontrollably. Stars form in waves that propagate along the filaments and disk, chains of ignition that follow the returning gas like fire racing along prepared fuses. And the supernovae from these stars, those brief, brilliant endings, add their own structured echoes. Their blasts compress nearby gas, triggering secondary births, while their debris is swept into the cycle, enriching without overwhelming. The cluster lives in layered rhythms: the slow breathing of the hot atmosphere, the faster pulses of the core, the brief flashes of individual stars, all nested, all synchronized by the central conductor. Another mesmerizing piece of evidence emerges from the motions of neutral gas, colder clouds that trace the skeleton of inflows without glowing fiercely. Radio telescopes detect these clouds in absorption, dark silhouettes against background light, or in emission from molecular tracers. In Phoenix, these neutral clouds form elongated structures that bridge the hot and cool phases, clumps condensing within the filaments, shielded by their orbital motion from full heating. They move coherently, following the same guided paths, some spiraling inward to seed the disk, others lingering in stable pockets where star formation smolders quietly. This multi-phase coherence, hot, warm, cool, neutral, all aligned, is extraordinarily rare. In less dominated systems, phases decouple. Hot gas churns, cool gas fragments, neutral clouds evaporate or collapse chaotically. Here the phases communicate, material transitioning smoothly from one to another under the central pull. Imagine gas as water in different states, steam filling the spaces, liquid rivers flowing inward, ice crystals forming in sheltered eddies, all part of the same current, shaped by one guiding force. Recent surveys have mapped these neutral structures in 3 dimensions, using velocity information to reconstruct their shapes. The result is a web of tendrils converging on the core, braided together like roots seeking nourishment, each strand contributing to the sustained flow. The web's stability over cosmic time demands gravity that reaches far, binding the outer clouds, preventing their dispersal by passing galaxies or internal turbulence. This far-reaching influence subtly affects the cluster's inhabitants. Galaxies on the outskirts show signs of aligned gas tails, not torn away violently but trailing gently, as if combed by an invisible wind from the center. Some tails curve inward, merging with the great rivers, donating material to the central cause. This organized stripping contrasts with the ragged chaos in ordinary clusters, where close passages rip gas away wastefully. Here, the process is efficient, contributing to the balance rather than depleting it. The central sovereign exacts tribute not through destruction, but through orchestration. As these outer connections come into focus, the light echoes, the neutral webs, the aligned tails, the full extent of the influence reveals itself. The black hole does not merely reside at the center. It defines the center, extending its reach across the entire realm, shaping dynamics on every scale. This pervasive influence challenges our compartmentalized view of cosmic environments. We once treated core, filaments, atmosphere, galaxies as semi-independent. In Phoenix, they are facets of one system, governed by one profound gravity. Theoretical models embracing this unity now reproduce the observations with striking fidelity. Simulations seed a cluster with ordinary ingredients, dark matter, gas, galaxies, then vary only the central depth. When the center is modest, the evolution follows familiar paths: rapid assembly, violent feedback, early quenching. But deepen the center dramatically and the trajectory diverges. Inflows organize early, outbursts sculpt rather than scatter, cycles establish and endure. The cluster retains dynamism, building complexity where others simplify into stillness. Phoenix matches this divergent path at every turn. And the most shocking discovery in these unified models is the emergence of self-reinforcing stability. Once the balance establishes, it resists perturbation. Inflows from mergers or cosmic streams are absorbed smoothly. Outbursts clear excess without breaking channels. The system adapts, maintaining its rhythm against external shocks. This resilience explains the endurance we observe, the cluster preserving its youth amid maturity, defying the usual drift toward entropy. It suggests that extreme central engines can stabilize vast structures, guiding them toward longer, more intricate evolution. The implications reach into the cosmic web itself, the filaments connecting clusters on even grander scales. Phoenix draws gas not just from internal cycles, but from these greater threads, tendrils of the universe's skeleton feeding the core. Observations hint at this connection, broader inflows aligned with the cluster's axis, as if the central pull warps the larger flow. Imagine the cluster as a heart in a greater body, pumping cosmic blood through its veins, sustained by the sovereign beat within. Ongoing missions probe these connections with ever greater sensitivity, mapping faint gas beyond the cluster bounds, tracing velocities that link local to universal. Each new dataset strengthens the unified picture, a realm governed by one exceptional force, where every element serves the sustained harmony of creation and power. The accumulated evidence, from innermost orbits to outermost echoes, now forms a complete interlocking whole. No aspect stands unexplained. No contradiction remains when we accept the central scale. But this completeness marks a turning point. Because the observations alone, no matter how compelling, point toward something larger, a theory that encompasses not just Phoenix, but the full range of cosmic possibilities. The most profound revelations emerge when we step beyond description into explanation, when we confront the ideas that make sense of this new king and predict the shadows it casts across the universe. These proofs indicate far beyond the cluster's glowing heart. They lead to a reevaluation of how the mightiest forces in existence can coexist with the most vibrant creation. The stage is set for the bigger picture, one that forces us to rethink the foundations of power, growth, and balance in the cosmos. The journey ascends, the vision expands, and the true terror and wonder of this sovereign monster begin to eclipse everything we thought possible. The echoes linger across the cluster like whispers from a distant storm, structured rings of scattered light that trace the rhythmic pulses of the central heart. These ghostly halos, the neutral webs bridging phases of gas, the gently aligned tails trailing from passing galaxies, all of it speaks of a realm governed by one overwhelming presence, a force that reaches outward with subtle but unbreakable authority. But let us explore yet another layer of this intricate tapestry, the subtle warping of light from far beyond the cluster, bent by the immense gravity at its core. Imagine rays of light traveling across the cosmos from distant galaxies, journeys that have lasted billions of years longer than the age of our own sun. As these rays pass near the Phoenix cluster, they curve, distorted by the deep gravitational well concentrated at the center. This bending gravitational lensing acts like a cosmic magnifying glass, stretching background objects into arcs, rings, and multiple images. In ordinary clusters, lensing is strong but distributed, shaped by the combined pull of dark matter, gas, and scattered galaxies. Here, the lensing patterns are unusually sharp, peaked dramatically toward the core. Background sources appear warped in precise alignments, their distorted shapes concentrating around the central palace rather than spreading evenly. This sharp peaking betrays a compact, dominant mass at the heart, one whose gravity overwhelms all others, focusing the lens with pinpoint intensity. Visualize faint, distant galaxies smeared into elegant arcs that encircle the cluster center like crowns of light. Some appear duplicated, mirrored images created as light takes forked paths around the central depth. Others stretch into thin filaments, elongated by the tidal pull. These lensed features are not chaotic. They align with the inner structures we've traced, arcs paralleling the jet axes, rings echoing the expanding shells, distortions strongest along the cool river's directions. This alignment reveals the central influence extending far beyond the visible gas, warping spacetime itself in ways that guide even unrelated light from the deeper universe. Recent studies have mapped these lensing effects in exquisite detail, combining deep optical images with gravitational models. The resulting mass reconstructions show a steep central spike, far sharper than in comparable clusters. The bulk of the lensing power traces to a tiny region at the core, demanding a single, profound anchor rather than diffuse contributions. This compact dominance stabilizes the entire cluster against external tides. Passing groups or cosmic flows should leave asymmetric scars in the lensing map. Here, the patterns remain remarkably symmetric, as if the central gravity smooths disturbances before they can take hold. Imagine the cluster as a vast lens held steady by an unseen weight at its center, light from the universe beyond focused cleanly, distortions controlled rather than wild. This control extends to the faintest signatures, weak lensing from the cluster's outskirts, where gravity subtly shifts the shapes of countless background galaxies. Statistical analyses of these tiny distortions reveal a halo of mass that hugs the visible structures tightly, lacking the extended, fluffy envelopes seen elsewhere. The tight binding suggests early concentration, gravity gathering material inward efficiently, preventing sprawl, building density at the heart. All these lensing clues, the sharp peaks, the aligned distortions, the symmetric patterns, the tight halo, interlock with the dynamics we've explored. The same profound depth that organizes inflows and cycles also warps spacetime on grand scales, leaving its fingerprint on light from the cosmos beyond. And recent collaborations have pushed this mapping further, using multiple telescopes to layer lensing data with X-ray, radio, and optical views. The combined reconstructions paint a unified portrait, a central sovereign whose reach permeates every scale, from inner orbits to intergalactic tides. This permeation challenges our separated views of gravity's roles. We once thought cluster assembly dominated by dark matter's broad scaffold, with black holes influencing only local cores. In Phoenix, the central gravity asserts itself across the full hierarchy, refining the dark matter distribution, steering visible evolution. Theoretical models incorporating this concentrated pull reproduce the lensing beautifully. Simulations that distribute mass evenly predict broader, softer distortions. Only when gravity spikes dramatically at the center do the sharp arcs and aligned patterns emerge. These models also reveal stabilizing effects. The deep well circularizes orbits early, damp substructure promotes symmetry. The cluster evolves into a poised, mature form while retaining youthful dynamism at its heart. This poised maturity is rare. Most clusters bear scars of violent youth, lopsided halos, tangled lensing, irregular gas. Phoenix appears almost sculpted, its harmony preserved by the central architect. Ongoing surveys hunt for similar signatures in other distant systems. Sharp central lensing peaks paired with organized inflows, symmetric patterns alongside persistent activity. Candidates surface, clusters where background arcs concentrate unusually, distortions align with inner jets, weak lensing hugs tightly. Each match adds to the emerging pattern, extreme central dominance enables unique evolutionary paths, sustaining balance where others settle into quiet. But the lensing evidence connects to an even deeper paradox. The immense gravity implied by these distortions should quench cooling utterly. Stronger pull accelerates infall, heats gas more fiercely, amplifies feedback. Yet here the opposite holds. The depth sustains channels, moderates cycles, permits creation. This paradox resolves in the refined regime we've traced. The same gravity that warps distant light also organizes local flows, binding return streams, directing outbursts, enforcing measured rhythm. Power at this extreme becomes not overwhelming but calibrated. The most shocking implication arises when we consider the cluster's place in the cosmic web. Lensing maps reveal faint bridges to neighboring structures, warped light tracing broader filaments of dark matter, and gas feeding the cluster from afar. These bridges align with the internal rivers, as if the central pull extends its guidance to the universe's larger skeleton. Imagine the cluster drawing sustenance from cosmic threads, its sovereign gravity channeling inflows efficiently, turning potential chaos into sustained nourishment. This far-reaching draw explains the richness we observe: gas reserves that replenish despite colossal consumption, starburst fuel that persists against expectation. Observations probing these outer connections detect subtle velocity shifts in intergalactic gas, material streaming inward along preferred directions, accelerated gently by the distant but profound well. The influence spans distances that dwarf the cluster itself, subtly steering the flow of matter across the void. As these outermost signatures come into view, the sharp lensing, the aligned cosmic bridges, the guided intergalactic streams, the full scope of the central presence reveals itself. It is not confined to the core or even the visible realm. It shapes spacetime, matter, light across vast expanses. The accumulated observations now form a seamless whole, from the serene inner disk to the rhythmic echoes, from the organized rivers to the warped distant light, every detail consistent, every paradox resolved by one extraordinary scale at the heart. This completeness signals the end of mere description, because the evidence no longer merely describes an outlier. It demands explanation, a theory that embraces the extreme, that reveals how such sovereignty emerges and what it means for the universe at large. The most profound discovery lies in this convergence. All paths lead to a central engine that has transcended limits, achieving a balance where immense power serves enduring creation. These revelations point far beyond the glowing cluster. They illuminate hidden possibilities in cosmic evolution, pathways where monsters become guardians, where regulation fosters rather than forbids. The picture is nearly complete in its evidentiary phase. The consequences cascade, linking this one realm to broader truths. We approach the moment where observations yield to interpretation, where the new king stands fully revealed, and we confront the bigger picture it demands. The wonder deepens, the implications expand. And the true majesty of this cosmic sovereign prepares to reshape our understanding of reality's deepest engines. We have traveled far together, across billions of light years to the blazing heart of the Phoenix cluster, through layers of scorching gas and cool rivers, past sculpted voids and ordered disks, tracing the fingerprints of a central power that defies every expectation. We have seen the evidence accumulate, observation by observation, each one interlocking with the next until no doubt remains. At the core of this distant wonder sits a gravitational sovereign unlike any we have known before. A beast so vast, so refined in its influence, that it sustains creation where it should enforce silence, sculpting its realm into enduring harmony rather than quiet submission. And now, as our journey reaches its end, we must confront the deepest truth this discovery reveals. Everything we have witnessed, the persistent starburst raging against cosmic logic, the rhythmic cycles of outburst and renewal, the guided flows that turn violence into nourishment, the sharp warping of distant light, all of it points to one unifying reality. Phoenix A is not merely an outlier. It is the exemplar of a hidden extreme, a black hole that has crossed into a realm where power and creation coexist in exquisite balance. This is the theory that explains it all. In the richest environments of the young universe, dense peaks where galaxies collided frequently and gas streamed abundantly, certain black holes could exploit every pathway to growth. Mergers delivered sudden leaps in mass. Aligned inflows allowed sustained accretion beyond ordinary limits. Outbursts far from throttling progress sculpted channels that enhanced future feeding. Spin amplified efficiency. Magnetic fields anchored stability. most seeds hit brakes and slowed. But in rare, perfect conditions, a few broke through, accumulating scale rapidly, entering a regime where feedback shifts from suppression to calibration. At this extreme, gravity deepens profoundly. Inflows organize early. Cycles establish rhythm. Outbursts direct rather than scatter. The system self-stabilizes, resisting chaos, sustaining both quiet growth at the center and vibrant creation around it. Phoenix preserves this regime in living form. Its central engine, vast beyond precedent, orchestrates the entire cluster, calming orbits, guiding rivers, moderating pulses, enabling the greatest starburst ever witnessed. Alternative explanations falter here. Modest central masses predict swift quenching, fragmented flows, erratic activity, none of which match the poised harmony we observe. Exotic mechanisms, delayed feedback, unusual geometry, transient phases, cannot sustain the endurance, the symmetry, the multi-scale coherence. Only the ultramassive paradigm fits every detail. Key researchers, from teams behind Chandra, Hubble, ALMA, and the James Webb Space Telescope, have converged on this view in recent years. Collaborations modeling cluster evolution now routinely include extreme central engines as viable outcomes. Philosophically, it forces us to rethink foundations, black holes not as endpoints of destruction, but as architects capable of extended guardianship. This forces us to reimagine our place in the cosmos. If such sovereigns exist, shaping vast structures with measured power, then the universe harbors greater diversity, deeper possibilities than we dreamed. Creation can persist longer in the shadow of monsters. Balance can emerge from extremes, and the future promises answers. Upcoming missions, upgraded X-ray observatories, next-generation radio arrays, gravitational wave detectors sensitive to low frequencies, will probe deeper. They will map hidden populations, catch merger echoes of titans colliding, resolve cores in distant clusters with unprecedented clarity. Breakthroughs in simulation will trace growth pathways from cosmic dawn. New lenses will hunt sharp central peaks across thousands of systems. Each advance brings potential to confirm the hidden realm Phoenix reveals or refine its boundaries. We stand on the cusp of knowing whether ultramassive black holes are rare curiosities or quiet shapers of the cosmic landscape. Recent hints from other clusters, persistent cooling in a handful, oversized cavities in others, give grounds for optimism. The evidence mounts that Phoenix is not alone, yet the deepest questions remain. What ultimate limits, if any, constrain these sovereigns? Could even grander extremes lurk in the universe's most obscured corners? Stupendously large black holes influencing entire superclusters. How do they alter the chemistry of space, the distribution of elements, the potential for life in their realms? Consider the scenarios. In one future, surveys reveal a spectrum, most clusters governed by ordinary regulation, a few by permissive balance, Phoenix at the luminous extreme. Cosmic evolution gains nuance, diverse outcomes from shared origins. In another, ultramassive engines prove common in the early universe, their signatures faded in nearby systems. They seeded metals rapidly, built dominant galaxies, stabilized vast structures, quiet architects of the universe we inherit. In a bolder vision, these sovereigns connect to primordial origins, direct collapse seeds from the Big Bang's aftermath, grown unchecked in dense voids, preserving relics of the universe's first breaths. Or perhaps the rarest path, objects pushing theoretical ceilings, where gravity warps reality in ways we barely grasp, frame dragging on cluster scales, horizons vast enough to engulf light from entire epochs. The deepest insights emerge when we consider the paradox at the heart, power that enables rather than forbids. In Phoenix, the monster nurtures the garden, destruction serves creation, regulation fosters complexity. This duality mirrors the cosmos itself, birth from collapse, light from darkness, order from chaos. Phoenix reminds us that extremes do not always simplify, they can enrich. Current scientific consensus leans cautiously. Phoenix A is extraordinary, its central mass likely among the greatest known, its feedback regime unique but physically plausible. Debate continues on precise scale, estimates range wide, but agreement grows that it challenges old ceilings, demands new models. What we have learned is profound. The universe permits sovereigns that reign through balance, not brute force, monsters that sculpt beauty from their roars. And what remains mystery is vaster still. The full population of hidden titans, their role in cosmic history, the ultimate boundaries of growth. We began with a provocative truth. A new king has risen, vast enough to swallow worlds whole, yet coexisting with the greatest stellar frenzy ever seen. A beast that should silence creation but instead sustains it. We have followed the evidence across every scale, from innermost orbits to warped distant light, and arrived at a new wisdom. The throne of cosmic monsters belongs not to the most destructive, but to the most masterful. Phoenix A is that master. In the end, the universe remains unbound. Its extremes stretch beyond our grasp, its possibilities infinite, and our journey through wonder, paradox, revelation has shown us that even in the darkest hearts, creation can thrive. The stars continue to ignite in distant fires. The rivers continue to flow. The sovereign watches, balanced on the edge of eternity. And somewhere in the vast silence between galaxies, new kings may yet be rising. The universe is profound, its secrets endless, and our quest to understand it eternal. Thank you for joining this journey. The story of Phoenix A, of the new king of monsters, is only beginning.